Hello, everybody. This is the fourth part of the chapter 1.3 series, and we will talk today about linear combination in Rn. So we were building up, looking at one-dimensional spaces, two-dimensional spaces, and now we're ready to extend our findings into the any dimensions, and can be absolutely any number. So let's look at the basic definition of the linear combination. You probably find that this first part of this definition look exactly as the second part of our series for the two-dimensional space. We just keep adding vectors multiplied by their weights, C. So we can have as many vectors as you want. We just need the weight assigned for this vector, and we'll call it a linear combination. Okay, and this is where we are kind of limited with geometric interpretation. Two-dimensional space is pretty much as far as you can go with pencil and the sketching things out. So we are limited with an actual number here. So let's just try to look at how we can work with our linear combination of vectors. So let's take three vectors, A1, A2, and B. The question is it possible to write vector B here as the linear combination of vectors A1 and A2? And you probably kind of slightly confused here because before we were talking about vector V1 and V2, and I'm suddenly here switching to the A and B notation, which must be slightly uncomfortable. Bear with me, there is a reason behind it. So we are switching to our vector notation to A's. And since we're switching from V to A's, we can also switch to C to another variables. Let's call our weights X. So in this new variable, our problem reduced to we need to determine the weights, again, we call it x1 and x2, such that the linear combination of x weights x and the vectors A will give us a matrix B. Again, this is quite a mouthful. Let's just start by putting the numbers for our vectors and maybe we'll get somewhere. Okay. So let's take our weight x1 and multiply it by our vector a1. And then we continue with our linear combination. We take vector x2 multiplied by vector a2, and it should be equal the vector b. Okay, that's great. Let's conduct the basic vector operations and see what's happened. We distribute x1, we distribute x2. Although they are variables, they still can be treated as the numbers for the matrix operation. And b remains the same. So then we sum the like terms in the our matrix. And what we have here is very, very similar to what we saw in last class. So this is just the equation, three equations with two variables, and we seems to be looking for the solution of this equation. And since we've done it a lot of times, we can attempt it again. All we need to find x1 and x2. Okay. Let's make an augmented matrix of this system and see if we can solve it. Okay, this is our augmented matrix, and the best approach is reduce it to the echelon form. And to get it to the echelon form, we're lucky. We have first pivot element is already equal 1 here. We just need to get rid of -2 and -5. We need to use the row operation to convert them to 0. Okay, then the next order of operation, we should have a second pivot element here equal 1, but instead we have 9, so we can divide second row by 9. And now we have a second pivot element, but again, should be the rest of this column should be 0. So we should have a 0 in the first and a third row. And again, we conduct the row operation, multiply second column by 16, subtract from the third one, multiply second column by 2, subtract it from the first column, first row, and we'll get our nice echelon form matrix, which give us advantage of having solution right away. Our one pivoting element give us value of x1 is equal 3. Our second pivoting element give us value x2 is equal 2. We do not have any pivoting elements. However, our last row is equal 0, which can be read as 0 times x1, 0 times x2 is equal 0, which is absolutely valid equation. So we seems to have a unique solution. And this unique solution provides us with the weights x1 and x2. And again, this is the time to pause, look back to the problem. What are we looking for? We're looking for x1 and x2, because if we have x1 and x2, we can write down our linear combination. So, and again, we take weight x1 is equal 3 multiplied by the vector a1, take weight x2 is equal 2 multiplied by a2, and that give us our vector b. So indeed, this two vectors can be expressed as linear combination to find vector b. And you probably notice that this vector equations pretty much give us the same augmented matrix. So what we can do, we can actually skip all the second part and say, you know what? At the end, we would be looking for the augmented matrix. So what we could do next time is just take our vector a1, a2, and b and just directly construct the augmented matrix and find the solution in echelon form. Basically, this vector equation has the same solution, and we can extend this case for any dimension. So if we have a vector equation in any length, we can, instead of solving it, find the solution of the augmented matrix. Okay, that's all for the linear combination in Rn, and I see you soon in class.